It's easier.
Okay, thank you, Peter, for this nice introduction. I would like to thank Jan and all organizers for inviting me, to giving me opportunity to be here and present the topic of my today's talk, which is entitled Fiber Chip Couplers for Application in Silicon Photonics Optical Interconnects. My name is Daniel Benedikovic and I am with the University of Žilina from Slovak Republic. I will start my presentation by a brief introduction in the field of silicon photonics. Then I will follow in my presentation and talking about the interfacing of silicon chip with external ports, with particular attention will be dedicated to connection between silicon chips and optical fibers. During my talk I will present some recent approaches how to efficiently couple light between optical fibers and silicon chips. Two main approaches include fiber chip edge couplers and fiber chip surface grating couplers. At the end of my talk, conclusions and summary will be drawn. So let's start. Silicon photonics is considered to be a buoyant research field that can provide a lot of interesting and promising application, ranging from data centers, telecom application, to sensing. More recently, the main driving force for silicon photonics is in optical interconnects. The main aim is to replace copper solution with optical technologies. In addition to this, silicon photonics is the field that can provide extended spectral range, ranging from near infrared to the mid infrared and also to the long wave spectral range. However, silicon is not the best material for optics, in particular for generating light and detecting light. Silicon does not provide the best modulator, the best detector, and definitely not the best light sources. Making these devices in silicon is pretty challenging. But on the other hand, it has to be mentioned that silicon offers excellent prospect, especially due to microelectronic industry. In this way, silicon provides a lot of advantages for optical communications. Silicon is widely available optical material. Silicon is transparent material up to 8 micrometer spectral region. The prominent platform for silicon photonics is silicon insulator, when a lot of different devices, especially passive and some active, can be made. As I mentioned, silicon can take a lot of advantages from the complementary metal oxide semiconductor infrastructure. This is very major technology due to the lot of investments that have been made in microelectronic industry. In this way, silicon can provide a high volume production. In addition to these advantages, the cost of SOI, silicon insulator wafers, is pretty low. Silicon can provide also mutual integration of optical functionalities and electronic functionalities on the same chip. And especially a significant feature is the high index contrast between the silicon insulator waveguide platform, because it provides a strong light confinement, and in this way very small devices can be made. This also enables high integration density, and a lot of devices can be implemented on the same chip. The main topic of my talk is the interfacing of silicon chip with external ports. Coupling of light is considered to be a major challenge since the early years of, in general, integrated optics. Direct connection between optical fibers and very small silicon nanowires is very challenging. This direct connection poses impractical level of losses and therefore efficient connection between silicon chips and optical fibers is highly desired. This is especially due to the large refractive index difference between optical fibers and silicon nanowires, and the second issue is the mode size dimension. As you can see on these two figures, the mode size there is 2 orders of magnitude difference. The solution how to couple light efficiently is the utilization of mode size converters. Recent approaches to solve this problem include edge couplers and surface grating couplers. So, fiber chip edge couplers. We have here silicon chips, and here we have optical fiber, and we put the optical fiber near the edge, the chip, or the silicon chip, and we try, we would like to obtain the high efficiency between these two elements. Various solutions how to implement fiber chip edge couplers include lensed optical fibers or micro lenses, integrated mode size transformers that can be realized by mode expansion principle and also mode delocalization principle. So the simplest approach is implementation of optical fibers with some lenses. Here on the side of silicon chip we have some tapered converter, and optical fiber with lenses is positioned here, and in this way we can couple light from the chip to the fiber. The second approach is implemented by integrated mode size transformers that utilizes mode expansion principle. The propagating mode in the silicon waveguide is expanded in both transversal direction, that means in this way, along the width of the waveguide and along the height of the waveguide. We would like to have very high efficiency. Here you can see one of the representatives of this approach. It is called 3D adiabatic taper. On the side of silicon chip, as you can see, we have a very narrow waveguide, and by utilizing this 3D adiabatic taper, we try to expand the mode and match it to optical fiber, which is positioned here. On this figure we can see the fabricated devices. The second device that utilizes the same principle is called double stage taper. You can also see that the mode expansion is achieved in both direction by utilizing this kind of structure. However, it has to be mentioned that 3D adiabatic tapers and double stage tapers requires very complex fabrication, including grayscale, lithography, and large number of processing steps. This is very serious limitation for practical application of these devices. The next approach is implemented by using mode delocalization principle. The mode size in the waveguide is expanded by using inverse taper by adiabatic decrease of the waveguide width. As you can see on this schematic figure, the width of silicon waveguide is getting narrowed, and here on this side the optical fiber is positioned. This kind of devices requires very accurate fabrication, and the tip at the end of the chip needs to be at least 100 nanometer wide to be compatible with the state-of-the-art fabrication tools, for instance DUV lithography. Next approach that was developed in Canada in National Research Council by Dr. Pavel Heben is implemented by using sub-wavelength material structuring. This means that the silicon waveguide is structured with dimensions that can suppress the diffraction effects. In this way, light propagates from the side of the silicon waveguide to the edge, to the chip, and here the optical fiber is positioned. You can see on these figures from electron microscope the device structure. Here on this side you can see the sub-wavelength structured waveguide core that is directed to silicon chip, and in this way light is coupled from the fiber and traveling through the waveguide to the chip. In these devices, very low coupling loss has been achieved experimentally with minimal wavelength dependence. Okay, this concept has been recently followed by the US company IBM. This kind of edge coupler has been recently presented at an optical fiber conference in Anaheim in March during this year. As you can see, this kind of structure uses absolutely the same principle. The main difference is that IBM using V-groove where the optical fiber is positioned. The fabrication of this is quite complex. Achieved coupling loss is pretty good for practical application. This coupling loss was achieved also for both kinds of polarization, transverse electric and transverse magnetic polarization. Here I would like to summarize some main advantages of fiber chip edge couplers. This optical coupling structure holds promising prospect for efficient connection between silicon chips and optical fibers, providing sub-decibel coupling performance. These devices can operate in a broad spectral range, and also they provide very low polarization dependence. On the other hand, it has to be mentioned that this kind of devices requires very careful chip preparation, which includes facet polishing and accurate chip dicing. The chief obstacle for practical application of this kind of coupling structure is the fact that edge couplers do not allow testing of fabricated devices on a wafer scale level, which is very highly desired feature for high volume manufacturing. This obstacle can be obviated by using fiber chip surface grating couplers. The operating principle you can see on this figure. The interfacing with optical fiber is achieved by redirecting the light from the chip towards the fiber by using diffraction grating. Optical fiber interfaces the chip from the top, and in this way we obviate the need for chip polishing, and chip dicing can be obviated. Optical coupling structure realized in this way can be located at arbitrary position on the chip surface. Thus, in this way, devices and whole silicon chip can be tested by using wafer scale level, which is excellent for mass scale manufacturing. In contrast to edge couplers, grating couplers also provide relaxed fabrication tolerances, relaxed interconnection space on the chip, and additional capabilities for low cost and CMOS compatible integration and packaging. Some disadvantages of fiber chip surface grating couplers includes relatively low coupling efficiency, limited operational bandwidth, and very strong polarization sensitivity. In the next slides of my presentation, I will show you how we can achieve very high coupling efficiency by using this kind of coupling structures, and also how to address these obstacles. So, surface grating couplers are typically implemented by using lithographic definition. This means that in silicon chip we use some kind of optical lithography to define a grating. Conventional approach includes at least two fabrication steps. One step is used to define the grating itself, and the second step is used to define interconnection waveguides. More interesting approach has been proposed by Dr. Robert Halish from University of Malaga. They use sub-wavelength structures to modify the grating coupling strength. In this way, efficient grating couplers can be fabricated by using only one fabrication step. Sub-wavelength dimension, as you can see on this schematic figure and also on this figure, from our fabricated grating coupler are small enough, thus no diffraction takes place. Initial consideration in grating couplers includes grating couplers behavior can be readily described by the well-known Bragg formalism. This leads to the phase matching condition. In grating couplers, the input light from the silicon chip or from the optical fiber is scattered to all directions. That means that fiber, that light is traveling backwards through the grating, upwards and also downwards. Typical grating couplers are preferably designed by using first diffraction order to achieve very efficient coupling structure. Single beam radiation can be assured by proper choosing the grating period. Okay, one of the main figure of merit for grating couplers is their coupling efficiency, defined in this way. As I mentioned, there are several sources for coupling losses, including transmission losses, back reflection, mode mismatch, and grating directionality. The ideal fiber chip surface grating coupler would have ODB coupling efficiency, or in percentage 100%. That means that all light that we couple from optical fiber to the chip will be directed in the proper way. Okay. So, however, typical surface grating couplers currently have coupling efficiencies around -5 to -4 dB, which is not sufficient for practical application. In addition to this low coupling efficiency, as I mentioned, the grating couplers are strongly polarization sensitive, and also they provide only limited operational bandwidth, typically in the range of 50 to 60 micrometers. There are several ways how we can achieve very high grating coupling efficiency. There is a reduction of transmission losses, reduction of back reflections, improving the mode matching efficiency between the diffracted grating mode and the mode of the standard optical fiber, and improving the grating directionality. That means that we enhance the power that is radiated directly to the optical fiber, or we can reduce parasitic radiation towards the silica substrate. In principle, we would like to have coupling efficiency that is below 1 dB. This level is considered to be the desired level for practical applications. So, transmission losses can be reduced very simply by proper adjusting the edge depth in the grating region or using metamaterial engineered grating couplers. This is typically used in both types of grating couplers. And in addition to this, grating coupler must be sufficiently long. This can be achieved by proper choosing the number of grating periods. The serious issue in grating couplers is their back reflections. Back reflection can reduce overall coupling efficiency, can deteriorate the behavior of some photonic devices, especially lasers or amplifiers, and can increase the level of noise in the integrated circuits. There are basically two sources of back reflection. One is second order back reflection, and the second one is the Fresnel reflections. So, reduction of back reflection, second order back reflection, can be reduced by detuning the coupling angle. In typical grating coupler, we use quasi-vertical coupling. That means that optical fiber is tilted by some amount of degree. In this way, momentum matching for the second order diffraction can be suppressed. The more serious issue is the Fresnel reflection. Fresnel reflection can be reduced by improving the field matching between the mode propagating in the grating region here and the excitation stage which is here. In this way, we can significantly reduce back reflection. In grating coupler spectrum, we can see that back reflection are presented here by means of Fabry-Perot ripples. The second approach how we can alleviate the back reflection in grating couplers is implemented by improving the impedance matching between the waveguide and grating transition by using grating apodization. That means that we properly tailor the grating coupling strength along the mode propagation direction. In this type, we can apodize grating by changing the duty cycle, as you can schematically see on this figure, by changing the edge depth in the grating or by using variable sub-wavelength grating structure along the grating. Here you can see the fabricated devices by using these three approaches. Here you can see fabrication that was done in Singapore. They use two types of edge depth to reduce the back reflection. Here you can see some of our grating couplers that they are implemented by using sub-wavelength material structuring, and here you can also see the grating coupler that is implemented by changing the duty cycle. A very popular approach in recent years how to reduce back reflection is by utilizing the curving and offsetting the grating light to ensure that the back reflected light does not couple back to the access waveguide. This approach has been implemented by IMEC from University of Ghent in Belgium. As you can see, here we have access waveguide, and here we have the grating, and by changing the position of the access waveguide, we can achieve a very low level of back reflections. Okay, the next source of losses is mode matching efficiency. The mode matching efficiency can be straightforwardly improved by utilizing the non-uniform coupling structure. That means it is grating coupler that have variable coupling strength along the mode propagation direction. Uniform grating couplers have field overlap between optical fiber and the diffracted mode up to 80% and exponential decaying field, as you can see on this figure by this in this orange curve. Apodized grating couplers overcome this limitation. In this way, we resemble the profile of the diffracted grating mode and we match it to the Gaussian-like optical fiber mode. More than 90% mode matching efficiency can be readily achieved by simply changing the geometry of a grating coupler, and in this way we don't need to include some additional fabrication processes. However, in case of grating apodization, critical dimensions of grating coupler are typically at the limit or beyond the limit of DUV lithography. The critical dimension should be higher than 100 nanometer. As I mentioned, in the case of reducing back reflections, grating apodization can be implemented by duty cycle apodization, edge depth variation, or SWG grating coupler apodization, or also you can combine this technique to achieve proper matching. The most serious issue in case of grating couplers is the diffraction efficiency. Diffraction efficiency means is defined as the ratio between the power that is radiated upwards divided by the total outcoupled optical fiber. There exist three ways how the diffraction efficiency can be increased. We can use a custom design photonic substrate. In this case, probably we will require own fabrication facilities. The grating directionality can be optimized in extrinsic way by exploitation the constructive and destructive interference effect, or the grating directionality can be optimized intrinsically. In this way, we directly improve the upward radiated power while we reduce the parasitic radiation into the silicon substrate. Or, as I mentioned before, we can use combination of these approaches. Grating directionality or grating diffraction efficiency very seriously depends on the waveguide thicknesses. As you can see on this figure, the optimal region for grating coupler that have a very high diffraction efficiency is around 350 region. Thicker silicon waveguides can provide direct improvement in terms of grating directionality. The concept of using thicker SOI waveguides has been implemented, for instance, by companies like STM, Microelectronics from France, Luxtera, Oracle, or Molex from the USA. However, on the other hand, in Europe, especially in Europe and also in Singapore, silicon photonic foundries typically use SOI thicknesses with 220 micrometer waveguide thick silicon. In this way, the grating directionality is pretty low, below 40%. However, this kind of waveguide structures are typically utilized by silicon photonic foundries, which poses a way towards fabless silicon photonics. In addition, you buy your own place on the silicon chip, and this is a great opportunity for new players to design and develop your own devices. This fabless silicon photonic model has been implemented by European companies such as IMEC, CELET in France, IHP in Germany, or the company A-Star from Singapore. The second issue in terms of grating directionality is the thickness of a borate oxide layer. By changing the thickness of this layer, the constructive or destructive interference effect can occur at the interface between this box layer and the bottom silicon substrate. If we have constructive interference, we can have very good coupling efficiency, but on the other hand, if we have destructive interference, we can have very low directionality and very low coupling efficiency. By choosing the proper thickness of this box layer, we can directly improve the grating directionality, but at the expense of requiring non-standard silicon on insulator wafers. However, typical silicon insulator wafers that are proceed in silicon photonics application offer only a discrete collection of box thicknesses, typically 1 micrometer, 2 micrometer, or 3 micrometer, and the freedom of choosing a different one is very limited. This issue can be alleviated by optimization of grating coupling angle. By adjustment of coupling angle, the fiber chip diffraction efficiency can be readily maximized for arbitrary box thickness, different grating geometry, and also different spectral bands. We use this approach and we fabricated our grating couplers that provide very high coupling efficiency. These grating couplers has been fabricated by using electron beam lithography and inductively coupled plasma reactive ion etching by using only a single step process. We achieved very high coupling efficiency, which is actually one of the highest achieved to the date for surface grating couplers implemented in silicon insulator waveguides. We used a similar principle for grating couplers implemented for 1.3 spectral region, and also we achieved very nice coupling efficiency. The similar coupling efficiency has been achieved for a more complicated coupling structure. In addition, we performed some additional calculations to be sure that this concept will be compatible with DUV fabrication tools. Our calculations predict very high coupling efficiency at the level of -1.7, which is pretty impressive for single-step grating couplers. Okay, next way how we can increase the fiber chip coupling efficiency is by implementing the mirror structure in the bottom of the grating. Mirror deposition is typically implemented by removing the bottom silicon substrate by using backside processing followed by metal deposition, or we can use wafer-to-wafer bonding to create a dielectric reflector, as you can see on these two figures. Some of these approaches has been implemented, for instance, by CELET from France. By using wafer-to-wafer bonding, they achieved 1.6 dB coupling efficiency. In similar way, IMEC group from Belgium has demonstrated grating coupler with distributed Bragg reflector, and they achieved -1.58 dB, and the same group has demonstrated the combination of both approaches. They use wafer-to-wafer bonding, and the aluminum, not aluminum, but gold metal underneath the grating to increase the diffraction efficiency. In this way, the realization of grating coupler has been implemented by using a host substrate. The state-of-the-art grating couplers are achieved by the Silicon Photonics company Luxtera. They use their own custom design silicon insulator wafer. In this configuration we talk about double SOI structure because we have here two box layers. Here you can see this layer and this layer create a mirror. Thus the power that is radiated toward the substrate is constructively diffracted towards the grating and then towards the fiber. Luxtera has achieved very nice coupling efficiency below 1 dB. To be more specific, they achieved minus 0.75 dB coupling efficiency. The best grating coupler recently available in the field of grating in the field of silicon photonics has been achieved by the group from Denmark. They use wafer-to-wafer bonding, custom design SOI wafer. However, this process is not truly CMOS compatible, and also the fabrication suffers from some thermal issue in the process. They achieved 0.58 coupling efficiency. Alternative way, as I mentioned, is using backside processing to create very efficient grating couplers. The group of Germany demonstrated last year shallow edge grating coupler with ultra high coupling efficiency, achieving the level of minus 0.62 dB. We in University of Žilina, in collaboration with National Research Council of Canada and University of Malaga, we achieved in our single step grating coupler coupling efficiency of minus 1.68 dB. It has to be mentioned and pointed out that this process is truly CMOS compatible, and it is applicable for arbitrary silicon insulator wafer. There is an alternative way how to achieve ultra-high coupling efficiency. In this way, we improve the grating directionality intrinsically. We achieved direct improvement of power that is radiated toward the optical fiber, and we reduce the parasitic radiation to the substrate. This way, we can alleviate the strategies of backside processing or wafer-to-wafer bonding. This type of grating coupler exhibit only very low dependence of grating directionality on the box, as I mentioned before, which is very critical, and in principle this can be implemented for arbitrary photonic platform. High directionality grating couplers can be achieved by adjusting the edge depth in the grating region, by depositing additional overlayers on top of the grating structure, or by exploiting the blazing effect in the grating. So the first approach is adjusting the edge depth. As you can see on this figure from measurement, the coupling efficiency has been improved from 5 dB to almost 2 dB by proper choosing the edge depth. This grating coupler has been also fabricated by using only one edge step. The group from A-Star from Singapore has developed very nice grating coupler that has been fabricated by DUV lithography, and they achieved very high coupling efficiency of minus 1.5 dB. In this case, they use two different edge depths to diffract the more power from the grating. The second approach how we can improve the grating directionality is by using additional overlayers on top of the standard grating couplers. In our grating coupler we achieved very nice coupling efficiency close to -1 dB, and group from IMEC has achieved in their grating couplers -1.6 dB coupling efficiency. The last approach how to make very efficient grating couplers without backside processing or complication the fabrication process is by utilizing the blazing effect in the grating. This has been proposed for the first time by FEN, and they achieved very high coupling efficiency of -1.25 dB. As you can see, you just need to interleave two edge depths in a proper way to achieve constructive interference for power that is coupled upwards, and destructive interference that is coupled downwards. Very nice approach has been proposed by Dr. Ramos from University of Paris Sud. They use CMOS compatible process with edge depths that are typically used in silicon photonic foundries. In this way, they achieved a very impressive coupling efficiency of -1.1 dB. The next, I would like to talk about the polarization dependence of grating couplers. SOI grating couplers are typically very polarization sensitive, and this is because the effective index of the block flock and mode that is propagating in the grating region is highly birefringent. This yields in largely different coupling angles for TE and TM polarization. This poses a crucial issue for application in which polarization state of light cannot be controlled. Some solution for this issue exists. It is utilization of two-dimensional grating couplers or utilization of sub-wavelength grating principle. Here, a group from Germany has implemented the grating coupler, which is polarization insensitive, by using two grating couplers that are interleaved with each other. Grating can couple orthogonal fiber polarization into TE and TM modes, and this TE and TM polarized light are traveling in opposite direction. They achieved very nice coupling efficiency for both polarization at the level of -2.4 dB. Similar approach has been adopted by Luxtera in their customized silicon on insulator wafer. Also, they interleave two grating couplers to couple light with TE and TM polarization at the same time. They achieved -2.2 dB coupling efficiency for their polarization splitting grating couplers. By utilizing the principle of sub-wavelength material structuring, we can also achieve two very nice polarization independent grating couplers. This can be implemented by cancelling the effect of polarization dependence of the block flock and mode that is propagating in the grating region. The principle is very simple, because the effective index for TE polarization in the silicon part of the grating is higher for TE polarized light than for TM polarized light. On the other hand, by using sub-wavelength grating principle, the effective index in the grating trenches is higher for TM polarization than for TE polarization. In this way, we can achieve that the block flock and modes of the grating are near the same, and then the coupling angles can be also the same. Thus, we can couple light efficiently for both polarization. This concept has been implemented by Chinese group, and they achieved experimentally minus 6.5 dB coupling efficiency for both polarizations, and by using distributed Bragg reflector underneath the grating, they achieved almost minus 1.9 dB coupling efficiency. Okay, the last issue in grating couplers is their broadband operation. Typical bandwidth of grating couplers, as I mentioned, is 50 to 60 dB, which is sufficient for many applications. However, to contrast to edge couplers, grating-based couplers are pretty narrowband. The bandwidth of the state-of-the-art grating couplers is mainly limited by the strong dependence of grating coupling angle on the wavelength. Solution to this problem is a significant reduction of grating strength by removing a substantial amount of silicon from the SOI waveguide or using sub-wavelength material structuring. Here are some broadband grating couplers. This has been implemented by group of China. As you can see, the silicon insulator waveguide is patterned in significant way. The experimentally achieved coupling efficiency was minus 5.6 dB with a bandwidth of 73 nanometer, and their simulation also predict for their improved design coupling efficiency of minus 3.4 dB with improved bandwidth of 86 nanometer. Similar concept has been also implemented by another Chinese group. They use this concept in the focusing grating geometry. Their experimental result has achieved minus 3.5 dB with a coupling bandwidth of 80 nanometer. The best grating coupler providing a broadband operation has been achieved only numerically, and simulation predict 1 dB bandwidth of 290 nanometer, which is pretty impressive. As you can see, they use trapezoidal shaped grating coupler by using sub-wavelength material structuring. This very high also coupling efficiency has been achieved by optimizing the box thickness of the grating. At the end of my talk, I would like to say that silicon holds a promising prospect for a plethora of practical applications in which coupling interfaces are one of the much desired photonic functionalities implemented on silicon chips. Recently, there are two main approaches for interfacing silicon chips. That is fiber chip edge couplers and fiber chip grating couplers. Fiber chip grating couplers are preferred solution because recently they can provide some sub-decibel coupling performance. They also provide promising perspective for wideband and polarization sensitive application. In contrast to edge couplers, grating couplers provide capabilities for wafer scale, device testing, and mass scale manufacturing. At the end, I would like to acknowledge the organizers for inviting me, and thank you very much for your attention.
Thank you, Dr. Benedikovic, for a very interesting presentation that opened our seminar. And if you have some question, I think we can open the discussion for the moment. So please, go ahead. Yeah.
Oh, okay.
Okay.
First.
Sorry.
Do you have information about the application of this interconnect on silicon chips? What companies are advanced now in this area?
Actually, to the best of my knowledge, there are some companies in USA, especially as I mentioned for several times, Luxtera, IBM, and also Intel is working.
In Europe?
In Europe, I don't know. There are some research industrial institutes such as IMEC, CLT, and also group from Britain, from Southampton, for instance.
Okay. I'm not familiar with silicon photonics, but currently I'm planning to use Aster process to fabricate some silicon photonic device. And
Okay.
could you give me some advice? What is the easiest coupling technique with silicon photonics device and fibers?
The easiest coupling technique,
Yes,
I think,
easiest and low with low coupling loss.
I think you can use both approaches, but the grating couplers can provide significant benefits, as I talk in my presentation.
Well, what is the best at this moment?
Best, I think, grating couplers, because
Grating couplers with which one? You introduced several techniques.
It depends. If you have money, you can create your own device. You put it, you prepare layouts and everything, and you will pay for it, and they fabricate everything you want. But it depends also on money. But if you want, for instance, to have efficient singlet step, grating coupler, you can achieve very nice coupling efficiencies at the level of 4 or 3 dB. And this is, I think, very good for some research activities.
Okay, thank you very much.
Any more questions?
Yes. Regarding the improving the efficiency of the grating with the back chip etching and visualization, does it pose a problem of robustness of the chip? I mean, the oxide layer then is only a few micron thick.
Yes, I don't think this is not problematic, because there are very nice results, and people who are doing this kind of backside wafer processing have technique how to alleviate problems with this.
The thickness.
Yeah.
Okay.
But yes, as you mentioned, the thickness is very critical.
Any more questions? If not, thank you one more for the presentation.